morning to everyone. Can you hear me? Can you correctly see the screen?
Yes, we hear you.
Thank you. Right. Okay. So I think we can start. It's 4:30 sharp. And so it's really a great pleasure to have to welcome again Giovanna as our Quid Ultra colloquium speaker. Giovanna is very familiar with the department as she has been the Fermi lecturer in 2019, right before the COVID pandemic started. And so we are really very, very happy to welcome her back. And so Giovanna is an internationally recognized expert on planetary science and exoplanets. But actually, she has started her career as a theoretical physicist. She had a PhD in theoretical physics at the University of Turin. And then soon after, she moved to her current field of research as a fellow of the NASA Astrobiology Institute at Caltech, JPL, and then as a European Space Agency External Fellow in Paris. And finally, she moved to UCL, where she's currently the head of the group of astrophysics and the director of the UCL Center for Space Exochemistry Data. So, so Giovanna is the PI of Ariel, the European Space Agency next mission devoted to that will be launched in 2021, and that sees a lot of participants even from Italy, including people from this department. And she is also the co-founder and co-director of the Blue Sky Space. And actually, we're very curious to know more about this, which aims at creating next opportunities for science-based satellites. And among the many achievements of Giovanna, she's a PI of a ERC-funded program on exoplanets. And also she was awarded the Moseley Medal in 2011 and the Prix Monte Carlo Femme de l'Année in 2021, on top of being the Fermi lecturer here in Rome. So she has co-authored a huge number of papers, and I cannot probably list them all, or even a few of them. So I really thank Giovanna for having accepted our invitation, and I really look forward to her view on galactic planetary science.
Thank you so much, Raffaella. Can you hear me well, despite the mask? It's a great honor and it's a great pleasure for me to be back. Clearly, I love this department. I love La Sapienza. Many people working here with whom we have long-term collaborations. And so here is really an opportunity not only to tell you what happened in the past couple of years on top of COVID in the field of exoplanets, and in particular what I've been doing, but also it's an opportunity for me also to refamiliarize myself with the department and all the people that are working here. Okay, so for those of you who are not familiar with extrasolar planets, let's say that in the past couple of decades, we have understood that planets are really ubiquitous because statistically speaking, we have understood that there are as many planets as stars in our galaxy. Of course, this is a statistical estimate because we don't know yet there's thousands of billions of planets in our galaxy. But the number of confirmed planets around our stars, this is the definition of exoplanets, is increasing exponentially. And at the moment, we have a short of 5,000 exoplanets being confirmed with a number of facilities and techniques. Many of those are organized in planetary systems with multi-planet system. And there are already some moon candidates. So clearly, it's a very exciting field, a very new one. And I think part of the excitement is also the understanding that the solar system, which is the kind of prototype of planetary system we're all grown up with, thinking is being the paradigm of planetary system out there. But actually that sort of statement is wrong. We have understood, looking at our planetary systems, even just very basic parameters, such as the distance between the planet and the star, like you have in this graph here, that is giving astronomical unit, all the planetary radius, all these colorful dots are all planets being discovered around our stars, and you can see immediately that all these colorful dots are not necessarily overlapping with the planets that are in our own solar system. So I'm not trying to suggest that the solar system is rare. I'm just saying, clearly, we are not the standard model, if you want, of planetary system out there. And similarly, if you look at some of the orbital parameters, it looks like many of these planets are orbiting in quite eccentric orbits, as opposed to almost circular, as we have in a solar system. And so clearly we're seeing a huge variety in terms of planets and planet-star combination. And I think the question is why? Why we're seeing all this diversity, and why is the solar system as it is? The NASA Kepler mission that was launched in 2009 have provided the first, if you want, statistics of planets outside our own solar system, because it was the first mission really aiming at discovering a large number of planets. And it did very well in that sense. Using the transit method, NASA Kepler was able to measure the radii of many planets. And what it has discovered is, first of all, small planets. For small planet, I mean whatever is not as big as Neptune and Jupiter in our own solar system. They seem to be much more numerous out there, statistically speaking, than the big planet. And so if you look at this distribution, immediately the first information is that Jupiter and Neptune are relatively rare out there. And on the contrary, most of the statistics is pointing at planets that are smaller in size. But then on top of that, more recently, more observations of the stars, so the pulsars done with spectroscopy from the ground or through Gaia measurements, have pointed out that not only small planets are more numerous, but actually we're seeing this sort of bimodal distribution that was completely unexpected, where we have two peaks. And these two peaks seem to point at two groups. One group that is closer to the size of the Earth, and another one that, on the contrary, is pointing at objects that are in between the size of Neptune and the size of the Earth. And so, of course, as you can imagine, there is a huge literature right now trying to understand where is this distribution coming from. Is it coming out of formation? Is the formation that is sort of inducing this distribution? Or, as suggested by some people, is actually something that is happening later on the formation. And so in particular is more determined by the photoevaporation. So basically the interaction between the star and the planet. And this view seems to be supported by the fact that there is a slight difference in the distribution if you look at different types of stars. But it's really early days, and we don't really have a strong, robust evidence from observations to go one way or the other. But we need to understand what are these objects that some people call super Earths or transitional planet or whatever you want to call them. In a certain sense, the fact that we don't really have even a very clear name is indicative of our ignorance of what these objects are. We don't really know. What can we do to understand a little bit better planet formation? Well, I think again, very recently, there has been a lot of observations from the ground using in particular ALMA, but also direct imaging with some facilities like the VLT Sphere or Gemini GPi. And basically, we started to look at the structure of circumstellar disks, protoplanetary disks, which are basically the environments where the planets are forming. And not only, these are beautiful images coming out of ALMA, you can see some very interesting and complex structures of gaps and spirals and rings out there, something, again, we were not expecting. But also looking at the chemistry of these disks, the chemistry of the disks is extremely complex, and there is a huge variety. And so all of a sudden, we start to understand also the complexity of the environments where the planets are formed. And also from the solar system, more and more observations about isotopic ratios among meteorites or bodies in the solar system, like asteroids or comets or moons or planets, again, seems to indicate quite strongly that during the formation of the solar system, there has been a pretty strong division between the inner solar system and the outer solar system when Jupiter has formed. And that has determined a pretty strong chemical gradients between the inner solar system and the outer solar system. And also this information through isotopes seems also to be timed quite well by different isotopes. And so all this information from the solar system is also helping us to understand the peculiarity of the solar system and why potentially it was different from other situations. So going on, clearly all this is extremely helpful also to inform models of planet formation, because all of a sudden, because of this new evidence, models that were used in the past to suggest the formation of Jupiter type of planets in particular, they were discovered to be wrong. They are too slow in forming planets as big as Jupiter, whereas both the solar system and the sort of structure we see in ALMA seems to point to the very fast formation of Jupiter type planets of the order of 1 million or so. So really, really very fast. So it means that new theoretical ideas were necessary to start to understand this evidence. And going forward, clearly, ALMA will keep delivering this fantastic measurements for more disks. And later in the future, SKA might be quite interesting, in particular to probe, ALMA is looking in the millimeter, and so is delivering information about coal dust, which is sort of really small in size. But if you want to look at the people, so basically objects that are at the level of centimeter, and try to understand how they're distributed, and this is very important for planet formation, then you probably need some to go for SKA, so different type of measurements. So hopefully more evidence will come soon also for the formation. So what do we know about the planets that are already formed and are being detected by all these techniques? Well, so far I would say very little. For the planets that have been observed through transit, like the one discovered by Kepler, you know the size. If there were some measurements with radial velocity or astrometry or other techniques like TTV, you might be able to determine the mass of the planet. Then we know typically the distance between the star and the planet, because we have some information about the orbital parameters. And so you can estimate the temperature of the planet. But for most of the objects we are seeing out there, that's it. And in many cases, we don't even know the size or the mass. And so, as you can imagine, it's really hard to draw a conclusion. What you can start to do are diagrams like this one, where all these crosses are all the measurements in planetary radii and planetary masses where there are uncertainties so far. And basically, these measurements are telling us something about the bulk density of these objects. If you know the mass and the radius, you can calculate the density. But the density itself can be very degenerate as a parameter. And here you have overlapped some colorful lines, which are suggestive of the bulk composition of these objects based on the density. But actually, the degeneracy is huge, because not only many different composition of the interior can deliver the same type of density, on top of that, If you include parameters like the temperature, the age of the objects, you have a huge variation. So bottom line, density is okay as zero order, but you shouldn't really push too much your measurement to tell you something that is not really there. So clearly we have all these new questions for the next decades. Why the solar system is as it is? What are exoplanets made of? Well, was the weather like that is perhaps more of a British question, but why are they so diverse? Then this is definitely a more general question. How did they form? How did they evolve? And of course, we are also interested about their habitability. So an important diagnostic that we can use is the atmospheric composition of these objects, because if we can couple on top of the density of the planet also what is the composition of the atmosphere, and we can measure directly this composition, then to a degree we can try to work out what are the processes that were important for the formation and the evolution of these objects. Of course, it's complicated, as this diagram is trying to suggest. It's not really a straightforward thing. You see a composition and that's it. You have understood all the history of the planet. But in principle, if you don't have just a handful of objects, you have a large sample, and for all of them, you have all this information, then you might start to see some trends and work out what happens. And so disentangle the various processes that brought to the final chemical composition. So this is what we are trying to do. And I'm pleased to say that today we have now many different techniques and not just one. In particular, the transit technique is relying on the fact that the orbit of the object is inclined in a way that the planet at a certain point is passing in front of the star or going behind it. And if you are in this orbital configuration, then you can sort of play tricks, summing up or differentiating the star from the planet. And so in this way, sort of, we can separate the contribution from the star and the contribution from the planet. But of course, you need to have an orbit that is done in a way that you can do this kind of observations. You can also separate spatially the star from the planet using direct imaging. For doing that, you need some sort of device like a coronagraph or another nulling technique to really mask out the contribution of the star and focus on the planet alone. And this technique is starting to deliver impressive images like this one that you're seeing here. It is a real picture of a planet. And transit and direct imaging are very complementary techniques, because for transit, you're quite biased towards planets that are orbiting very close to the star. Clearly, you can't wait 1 year or multiple years before you have another transit. But for direct imaging, on the contrary, our current instrumentation is sort of biased towards looking at big planets, very warm and very young. And so clearly, we have a sort of division in terms of populations. But more and more from the ground, spectroscopy at high resolution is being used to understand the composition of these atmospheres. And as I will mention later on, what you can do from space and from the ground is quite complementary, and all these techniques are complementary. So we don't want to select one, we want to have all of them, because ultimately it's telling us a slightly different story. We are also quite lucky because in the next decade, on top of having a lot of instruments from the ground and from space dedicated to detecting new extrasolar planets with a number of techniques, we also have instruments from the ground and space that will be able to deliver much better observation with respect to what we have today when it comes to atmospheric composition. And so what I think is for this talk is to give you some examples of what we are doing today with current instruments, and more to show you our limitations, but also our aspiration. And then, of course, with the idea that we'll have much more performing general observatories like James Webb or the ELTs, but also dedicated satellites such as Ariel in the next decade. Okay, so just a few examples for planets that are discovered through direct imaging. You can do spectroscopy on top of detection of the planet. And so you can work out, in particular in the near infrared today, some of the molecules that are present in these giant planets. Typically, they are young planets. They still need to be warm in order to be picked up by this technique. And this is on the contrary, an example from the ground of some measurements done at very high resolution with some of the instruments that are currently being used. And as you can see from the ground, if you have good instrumentation, you can really measure very precisely some single lines. And so if you want, for instance, to measure atomic species or ionic species, such as the helium line, you can do it very well from the ground. From space, it's a bit of a hell because it's way too sharp. And so this is great, really, that from the ground, you're able to look at single lines, but also some molecules that have a very weak signature that sometimes are lost from space observations. So from space, I think most of the observations we have done so far were done using telescopes such as Hubble and Spitzer. And I would say about 60 gaseous planets, typically like Jupiter or slightly smaller, were done. Most of them are relatively hot exoplanets. Being made of hydrogen and being relatively hot, it means that these are relatively easy targets to look at, in particular with the transit or eclipse techniques. And without necessarily showing you too many examples, I would just say for most of the hot Jupiters or hot Neptunes being probed, on top of course, molecular hydrogen, you can find some signature corresponding to water vapor, in part because the near infrared, which is where the WSC3 camera on board our Hubble is probing, is quite sensitive to the water signature. So it's by no surprise that water is very abundant, and on top of that, you have an instrument that is a bit biased on that. And so clearly we are finding a lot of water. But we are finding also some hints of other molecules, and that needs to be confirmed, and also some clouds. So still a little bit limited, but it's there. And of course, ideally, one would like to try to already start some form of comparative planetology and seeing the differences among all the planets that are being detected. We tried to do that some years ago with a sample that back then was including about 30 Jupiters. We tried to look at correlation between planetary temperature and size and all sorts of parameters. Without going too much in detail, let me just say that we didn't see any correlation simply because A, the statistic is small, B, the observations are not ideal. And so it was a first attempt, but clearly not delivering any real result in terms of population analysis. But so now that the planet starts to be more than 30, this is just a very quick review of a paper that is coming out. If you start to increase the sample and you have more observations, then you start to see some trends. And whether or not these trends will be confirmed by future generation of telescope or not, we shall see. But I think it's already good to see that little by little we are seeing some of this correlation being present. And so clearly this route of trying to work out of a population some common behavior or some differences, or to single out some planets that seems to stand out for one reason or the other, seems to go somewhere. And so I think it's a very promising route in particular for the future. But of course, certainly, I am very interested, but I guess many other scientists are really very interested in these small planets, this sort of domain of super Earths, transitional planets of Neptune. And so clearly knowing more about these objects is something I really want to do. Now with Hubble, it's still very hard to do this kind of measurements because Hubble or other current instrumentation were really never meant to go to the 10 or a few tens of part per million of the flux of the star. So you really need to do a lot of analysis in order to extract this sort of signal. This was possible in the case of K2-18b, which is a planet, one of these transitional planets, 8 Earth masses. And what we got out was this nice signature of water vapor, which is quite interesting, not only because this planet is temperate, has a temperature that is not very different from the one on Earth from measurements and also from orbital parameters. But still, beyond that, it's very hard to say what this object is. It could be what has been classified as water worlds because the density is suggestive of an object that is lighter compared to a rocky type of planet, but it could also be a small Neptune. What we know for sure is that on top of water and vapor, there must be some lighter elements like hydrogen still present in the atmosphere. Otherwise, you wouldn't be able to see so clearly the signature of water vapor. But we don't know too much beyond that. And just to make the situation more complicated, the radius and the mass of the planet are quite precisely measured, but in units of the mass and the radius of the star. And the star is actually an M dwarf, and M dwarfs sometimes are quite tricky to measure and to make sure that you really have the right size and mass. There are a lot of modeling being involved. And so bottom line, it means that also the density of this planet has quite some uncertainties. So we don't know. I'm describing you all this just for you to understand the complexity once you get into the domain of planets that are relatively small and unknown. There are other examples that for the moment Hubble was able to probe, like these other super-Earths, another one that is temperate. In this case, we don't even know whether the atmospheric signal that you're seeing here is really due to the atmosphere of the planet or is the activity of the star. The star seems to be quite active, and so we can't really rule out that some of these modulations are actually induced by the star. And again, the wavelength region we're probing is limited, so we can't really say for sure whether this is really due to the planet or to the star. And just to throw in some more caveats to go for full disclosure, this is a very nice work that has been published by Lorenzo here about another super-Earth, GJ 1132b, which is a warm, again, super-Earth. We still don't know whether the atmospheric signal that was sort of published by a team in the US, it's really an atmospheric signal of an instrument. A very thorough analysis led by Lorenzo and others seems to suggest it's actually the instrument, or at least the kind of modulations that the team in the US was seeing seems to be due to the instrument. So again, this is just to say how complex are all these measurements. So this is why, coming back now at UCL, we have invested quite a lot for the next decade or so into an infrastructure, because in order to understand these atmospheres, one needs to have, first of all, much more performing instrumentation. That's a must. But you also need to have quite an infrastructure of models and data science technique in order to do a good job, because otherwise you risk to extract the wrong thing and to overinterpret some observations. And so in particular, the EXO AI team at UCL, coordinated by my colleague Ingo Wallman, has looked into many machine learning and AI techniques to extract signal out of this data in a way that is as objective as possible. So you don't have to look at the data and make some maybe plausible and maybe correct assumption about the instrument of the star or other potential effects, that you can use data science in many cases to separate the noise from the signal. It's not always possible, but when it's possible, clearly it's a step forward. And this has been done for a number of instruments from space on the ground now quite successfully, also direct imaging, to be able, for instance, to correct for speckles, which are typically some aberration that sometimes can be well, they can be interpreted as planets, but they're not really planets. They're just an instrumental effects. So clearly we will hear and see more about AI and machine learning in the next decade. And also when it comes to interpret not just one, but many planets, you really need to use all the power you can have out of Bayesian technique, deep learning technique, anything. Not only to be confident that the way you're interpreting the signal is correct, but also have a good understanding of the reliability of the signal you're interpreting. And so what you're looking at here are some posterior distribution with clearly their distribution, because most cases we don't have such a sharp actually indication of what is the composition. With current instrumentation, most of the time we actually have quite almost flat sort of coverage of the parameter space. But again, all this can be done today with spectral retrieval techniques, that's how they're called, and in particular TauRex, which is the retrieval technique done at UCL, is completely open source. All our tools are all open source, all available in GitHub. If any of you is interested, you can just go to GitHub. Lorenzo knows how to find all them, or you can drop me a line and you can download them and just use them. They are really made to be used. We're all very excited by the fact that later this year, in December, the James Webb Space Telescope will be launched. And we're talking about 6.5 meter telescope in space, extremely sensitive detectors in the infrared. And so clearly, if everything goes well, it means that this fabulous instrument will be able, in particular, to look at spectra out of these smaller super Earths, in particular the cold one, which are so difficult to be studied today with current instrumentation. So clearly there is a lot of expectation for the James Webb, quite rightly so. Just one slide and a couple of words about an initiative that in parallel to what is happening with James Webb and later on Ariel we're having. I am a fan of the fact that the more data we have, the better. And so with our colleagues some years ago, we have funded a company called Blue Sky Space, and the idea of Blue Sky Space is basically to help financing first, but also then paying industries like Airbus and our space industries that normally are building satellites to build basically ad hoc space satellites that can be used by the entire community. And the way we are financing this is through a very similar route that LSST, for instance, or other ground-based sort of initiatives are being financed. And so the capital is put in by some investors, and then you recover, they are recovering the funding through basically scientists who are buying into a survey. So this sort of survey mode that currently is very successful for ground-based instrumentation we are hoping to see something similar happening also for space satellites, because we believe that there is quite a lot you can do in space, even with relatively small satellites. In the case of Twinkle, this is the first satellite done by BSSL. We're talking about a 45 centimeter satellite in low orbit doing infrared spectroscopy, something that for space industries is, I don't want to say straightforward, but certainly not particularly challenging. And so again, the more the merrier. And Twinkle is on its way now, and Airbus and ABB are building it, and we are looking at the launch in 2024. So hopefully we will see this very soon. But of course, if you're interested in understanding a little bit better the statistics of exoplanet atmospheres, and so not really going just for the few chance like in particular general observatories will be able to deliver, because of course the competition is very fierce, but you really want to go to the hundreds or even thousands of exoplanet atmosphere being looked at, then you really need to have a dedicated mission. And the dedicated mission now is called Ariel, because we proposed a mission concept to the European Space Agency some years ago, and it was selected in 2018 to be the next ESA medium-sized mission. And finally, in November 2020, it was adopted to be the next medium-sized mission. Adopted means now contracts are being signed, money is on the table, and there is no way back. And so that is a big difference from selection, which is, okay, you're selected, but somehow the legal sort of framework hasn't really been put in place yet. So now Ariel is adopted, and we're looking for a launch 2029. We will be launching L2 together with another mission of ESA Comet Interceptor. And we're looking about a 1 meter class telescope, doing a simultaneous coverage between 0.5 down to 7.8 micron in the infrared. And the reason why we want to do that in one shot is because if there is any contamination from stellar activity or systematics, the last thing you want is to have different instrumentation and to patch them together like we're doing today, which is definitely wrong. And so clearly it will be extremely advantageous to have such possibility. And so Ariel will really go for the at least the 1,000 exoplanet atmosphere being observed in 4 years. And if we are extended, then this number can be much larger. We want to select both rocket type, gases, temperature that goes from extremely hot to close to temperate, different type of star. All the parameter space of the weird cases that I mentioned before. We really want to understand the big picture. That is the idea of Ariel. The Ariel Payload Consortium has gone from a relatively small team of scientists and engineers to a really big team of 500 scientists that have joined, and engineers. From 16 ESA countries, and we have now a formal participation from NASA and from JAXA. This is a picture that was taken before COVID. We don't have yet a new picture in person, but the next time we'll be able to do that, so clearly will show this growth. As I mentioned, one of the main science cases in a certain sense of Ariel is not to go, or at least, of course, to study individual planets, but really go beyond that and really look at population analysis, planets by the kilos in a certain sense, atmosphere by the kilos. And so we have, of course, done a lot of simulations, and in particular, Lorenzo and Enzo here from La Sapienza, and now also Andrea. They're really critical to success of the mission, because they are the one beyond all this all the simulations, looking at the performance of the mission and basically connecting the performance of the mission with what science case we want to prove. And so, for instance, we were able to prove before adoption that if you have some chemical trends of some sort, And we did some simple cases just to understand whether the mission was doing what we were expecting, such as, let's say that the water vapor is directly correlated with the temperature. Can we see that? And what you're seeing here is actually what is coming out of the simulation. So it's basically simulation are looking at a very large number of planets, how area would observe them, look at the error bar you can extract, use all your retrieval tool to extract abundances of the molecule, and then basically do these plots. And we were very pleased to see that it is the case. And so clearly, if these chemical trends are there, we'll be able to see them, which is a very good point. We will be able also to follow planets throughout their orbit. And this can be very useful if you want to look at some variability of the chemistry or the weather. And so to see whether as a function of phase curves, we can see these trends. And also, in particular for the giant planets, we want to be able to extract also the elemental ratios. So for instance, oxygen versus carbon versus nitrogen versus sulfur. If we can probe that with a certain level of accuracy, then we can have basically some formal links with the formation processes, hopefully bearing in mind all the complexity of the chemistry of the disks where this planet are forming. And then finally, just a final example for the small planets, if you know both the bulk density and on top of that, you know the atmospheric composition, then you clearly have a much clearer way to classify them and to understand whether there are water worlds or sub-Neptunes, big rocky planets, and there are many molecular but also ionic sort of indicators that we can try to probe to understand what kind of class of planets we're looking at. This slide is just to say that we don't want to forget the ground. We are aware of the fact that not everything can be done from space. From space, you can do very well a large number of planets, because of course you don't have the cycle day-night to account for. You don't have the weather of the Earth to account for. And you can really probe a very broad range in one shot. But from the ground, you can go for very high resolution, and especially with ELTs, this very accurate measurements could really provide some complementary information about potentially even some isotopes in some cases. So I think it's great to include the ground. We will be extremely open with ERA in terms of data release and data policy. Most of the data will be out either immediately after quality control is done, or in just a much more, relatively small fraction after 6 months or so. So we really want to have all the data open and out to the community as soon as possible. And in the meantime, of course, being aware of how important it is to do a proper job in terms of data analysis, we are already training not just ourselves, but also the community to think about how we will be able to look at this data in a very sophisticated way when the data are out. And so we launched in 2018 the challenges that now has become a data challenge series in collaboration with the European Conference on Machine Learning. And in these two editions, the one of 2018 and 2021, more than 100 international teams have participated. Most of them were either amateur or professional machine learning scientists, in some cases many students. And then, of course, they were awarded. And it was really a learning experience. We have papers out about the techniques that have been suggested. And clearly it's paying off because we are learning quite a lot through this exercise. We're also quite involved in many citizen science programs, in particular the EXO clock that was started some years ago by Angelo Stiares, who was at UCL until recently, is now in Florence. but also with the help, in particular, Lorenzo on the Italian side, the ExoClock initiative is now counting for almost 300, Lorenzo? What is the number? Yeah. Yeah, we have scientists, amateurs, students, everybody contributing to monitor all the targets that will be helpful and interesting for Ariel. And so again, this initiative is becoming extremely successful with the participation that is really worldwide. So I believe my time is over, so let me wrap up the conclusions here. Exoplanets are really ubiquitous in our galaxy. And although the number of extrasolar planets is increasing exponentially, unfortunately, we still know very little about them. I think to fix this fact that we still don't have a complete understanding of the basic parameter of these planets, we have a number of techniques now, but also dedicated instrumentation from space on the ground to discover more and more interesting planets in the next decades. But also, if you're interested in planet formation, as I mentioned, ALMA and SKA and direct imaging from the ground will be quite critical to give us some more understanding of the environments where planets are forming. And then I hope I convinced you that looking at the atmosphere, at the atmospheric composition and structure, it is very important to understand the nature, but also the history of the planet. And in that sense, the launch of James Webb later this year, our satellites like Twinkle, but most importantly, I think dedicated mission on Ariel will be really an enormous step forward to understand all this diversity of planets that we're seeing out there. And I will finish just reminding everybody that these planets are still very far away, so we can't really travel there. And so we should all take good care of these planets, because for the moment, we don't have a plan B. Thank you very much.
Thank you, Giovanna. It was really a great talk, really, and also for this last message. So I would ask, first of all, the students here if they have any question for Giovanna, and then I will ask Angela to check if any question from the chat or from people listening. Just one to raise their hands, and we'll ask their questions. So any question from the audience here? Curiosity? Alessandro? Please, you have to really speak out.
Oh, okay. I was wondering how much the current statistics on exosolar planets might be biased by the methods of detection methods that we have actually, like this double peak distribution that we should.
Did the people from that are attending remotely understand could you understand the question was how the methods of detection can bias our understanding of exoplanets?
Definitely, there is a huge bias connecting to the techniques you're using to discover them. What I think is something that is the evidence that the planets in our solar system are not as diverse as what we're seeing out there. This is a fact, because otherwise you wouldn't fill this parameter space in this way. But I'm not suggesting that the planets in our solar system are rare, because if I look at this diagram, I know that there are still some areas that are not covered, but this is probably due to a bias in detection techniques. With direct imaging, we're able to probe even far out in terms of distance to the star. And I think the last data release of Gaia should be able to provide many more targets in this intermediate sort of distance. So I think this diagram will evolve actually quite soon towards something that is a little bit less biased. But still, in particular, when it comes to small planets, the bias will be there for a while, because not all techniques are as sensitive as others. When it comes to the fact that small planets are more common, that is not just out of transit techniques, it's also out of radial velocity, but also microlensing. And microlensing is very different, it's very complementary to radial velocity and transit. And so in a certain sense, the fact that small planets are so numerous seems to be quite a fact. The bimodal comes out of transit and is looking at planets with an orbital period that is less than 100 days. So in that case, of course, we might be seeing a selection effect connected to some form of bias. But clearly we need to explain that even in the context of this specific bias. So it's still an open question.
Is there any evidence for a segregation in the atmospheric composition of the two peaks? Do you have enough data for that?
We don't have data, that's the thing. For the moment, in these two peaks, for most of them, we don't even have the mass.
Okay.
And so we don't even know exactly what the density is. And in a few cases, we have the mass, but definitely we have no information whatsoever about the atmosphere, with the exception of this handful of cases that I was trying to present, which are on top of that quite incomplete.
Sure.
And so it's very hard today to point at one peak or the other and saying this is what is happening. Again, there are some quite hard debates in the literature at the moment, but they're not backed by the evidence at this point.
Not yet.
Not yet.
So I saw that there was a question from remote, from a remote attendance. I didn't see the name. I saw just the the hand that was raised. So
should I look into that?
yeah, maybe we can.
Hello.
Yes, please go ahead.
Yes, so my question is, how can we differentiate between brown dwarfs and hot Jupiters?
Excellent question. If you know the mass of the planet, then there is a sort of nominal distinction that is around the 13 Jupiter masses. Of course, it's very nominal and it's a bit of a gray area. But of course, if you don't know the mass of the objects, like for instance, the objects that have been discovered through direct imaging, you don't necessarily know the mass of these objects unless you have some astrometric measurements to constrain the mass. The only thing you're measuring is the luminosity of the object. And then you sort of have to model somehow the orbital configuration to have some extra constraints. But most of the time you can't really say this is a Jupiter or is a brown dwarf, there's a bit of a gray area. But if the mass is measured, then of course things are slightly clear.
Just another question.
Yeah, please go ahead.
So just can you comment about the free floating planets that are reported to found in recent years?
So your question is about free floating planets, is that correct?
Yes.
Yeah.
There are some paper published that are reporting there are free floating planets being found in our galaxy.
Yeah.
So are these planets that are through some process being ejected out of newly forming protoplanetary disks?
That's a great question, and the answer is we don't know. These free floating planets are objects without stars, and so being so dark, they can be detected only through microlensing. And through microlensing, you are able sometimes to constrain some parameters, not always with the kind of level of uncertainty you would like to. But it is true that they seem to be there, whether they're coming out of a planetary system because they were ejected through the formation and evolution process, or on the contrary, they formed as a star or brown dwarf might form, but simply with a smaller mass is hard to tell. But of course, they're very interesting objects because they are suggestive of some formation process. And so, again, knowing more about that might tell us something about formation of planets in general, or objects that are not really planets, but close enough.
But are we allowed to call them planets? Because I thought that one of the criteria to call a planet is that it has to orbit around another body.
Well, if you want to follow the IU, then of course
So
you
then
should
you
be
take the
careful.
liberty.
If you're a little bit more cavalier in your definition.
Okay. Any other questions? Ruggiero?
In one of your first slides, you showed that just one moon has been discovered today. And was it an exceptional measure? Was it something peculiar? Why did we discover this particular moon? And do you expect that we discover other moons in the near future?
Can you repeat the question?
Yes, so the question was about the moon candidate I mentioned in one of my slides, and what was special with this potential detection, and are there any hopes of more exomoons being discovered in the future? Very, very interesting question. I didn't have time to dwell into exomoons, but there are teams that are looking for exomoons since a while. And in particular, this moon candidate comes out of the team of David Kipping at Columbia University. And the way they have suggested that there might be a moon is because they were looking at some Hubble data, the planet, the host planet, and the candidate exomoon are both transiting. And so they saw a signal that could be compatible with the presence of an exomoon. The caveat here is actually the moon is as big as Neptune. So it's
a big moon.
It's a quite heavy moon. So whether then, in the case this is confirmed, we want to call them a sort of binary planetary system or not, I don't know. There were some controversies with the analysis of the data. Of course, these are very difficult data, and the signal is whatever it is, and so it's not really conclusive. But there are many techniques in principle to find exomoon, and the fact that they haven't been found so far is, I don't know, either exomoon are rare, or maybe the level of precision that we thought we needed is actually not enough.
Or these big moons are rare.
Yes,
That's a third option. So, any other question from the remote audience? No? I have another one. So, I mean, what would be the first program with JWST?
Okay, so the first program we did oversee is a program that is called ERS, the early, I forgot what the acronym is for. Anyway, it will be for a number of Jupiter-type planets. Maybe there's a Neptune in. So planets that, in a certain sense, were very well studied by Hubble, but again, Hubble was limited, and so the first step forward, which to me makes a lot of sense, is to study relatively deep in detail these few cases that were selected from community effort. And so doing a one-phase curve of a planet that was already observing phase curve with Hubble, doing some other observation, transit eclipses on some others. So it will be a limited sample, but very important one, because it might tell us something about objects that we were speculating way too much about.
But in perspective, it will open another, part of the parameter space, or it will allow a better understanding of the planets that are already known, or?
My suspicion is that it will open a new parameters, because it's all well to say that so we know what to expect, but at the end of the day, we don't. And saying that for 60 planets, we're seeing water vapor and some other molecules, the error bars and the abundance are so large that it's very hard to say anything constructive. And also all the models that today we have with the chemistry that seems to be okay and aligned with the very poor measurements we have. If the measurements are much better, then at that point we will see whether what we thought might be happening is true or not. And if not, then I would imagine an open new doors. I really suspect it will be the case. So I'm looking
Many
forward to
different
that.
things, hopefully. That's the
But later on, of course, I know that there are many more geo programs and more on steroids. And at that point, it's even more uncharted territory. So at that point, it will open even more.
So, c'è un'altra domanda? So, please go ahead from the remote. Yeah.
Yes, so far have we found any correlation between the spectral class of the host star and the exoplanet?
Yes, the answer is yes. We certainly saw a relatively strong correlation between the presence of large planets like Jupiter and Neptune and the metallicity of the star. But this sort of correlation seems not to be there when you're looking at smaller planets. So again, it's suggestive of the fact that if you need to build a big planet, you also need to have a lot of material, high Z material. And so you need to have a star that is relatively matter rich. But when it comes to smaller planets, perhaps these constraints are less strong because you don't need to have so much material. So this is one thing that it was noticed. And then a few others, but nothing really as dramatic to say, okay, that's it. We understand, we look at the star and we will know the planet. There's certainly a correlation between the mass of the planets and the mass of the star to a degree. So M dwarfs normally very rarely are showing big planets around them. We also noticing that there should be a preference for instance, if stars that are hosting many super Earths, they don't necessarily have giant planets and things like that. But we don't really have a big picture to understand all of this for the moment.
Interesting. So if there are no further questions.
Yes,
Yeah.
so on the back of this, the first ever exoplanets reported were in 1992. These were reported through pulsar timing. So how come exoplanets are orbiting around pulsars?
Yes, of course, I have to apologize in my seminar.
Because, sorry to interrupt, because in this case, the pulsar was actually earlier exploded as a exploded itself as a star. So how did this exoplanet survive the explosion of the host star?
It's a very good question. I haven't really mentioned pulsars at all. Again, I follow a little bit more the atmosphere here. But it is true that a sizable number of exoplanets have been found around pulsars. And of course, the big question is, were they there before the pulsar became a pulsar for a dramatic explosion or not? And we don't really know. It's definitely, I mean, it's not just the birth and formation of exoplanets interesting, it's also the death to a degree, or late stages of the life of exoplanets interesting, but also that is as obscure, perhaps even more obscure than the birth. So there are theories, but nothing being confirmed of what might have happened.
Interesting. So I would really thank Giovanna again for this. The people having attended the seminar, and we'll meet again for the last 2021 Creduta colloquium in December. So goodbye to everyone.